The following information was gathered and put together by Amir Jamal and Altaf Rahimi. This video presentation is based on our Structures 2 assessment, based on designing different elements of a domestic shed. When designing a domestic shed, there are many sectors of the design process which must be assessed correctly. This calculating the three main types of loads which have a major impact on the structure of a shed. The live load, which is the occupants of the building, which doesn't necessarily have a great impact, as well as the other two loads, dead load and wind load. Wind loads are extremely important as they impose suction and compression loads on the structure. These loads must be taken into strict consideration as it will determine the strength of the building. The aim of this report is to inform about the alternative design for structural members of an industrial shed. To achieve this report successfully, analysis of the members were conducted to ensure their strength under the imposed forces of live load, dead load and wind load. When designing a structure, a variety of resources must be used, including engineers' research programs such as space gas, to determine all potential forces applied to the building. In part A of this assignment, the initial task was to determine the wind load on the building. Thus, we had to design the wind speed and find the net pressure coefficients for suction and pressure. These tasks were both completed using the AS 1170 2011 and the AS 4055 2012. These provided us with wind regions, terrain categories, topographic classes and shielding classes, all of which aided in determining the wind class classification of our site. Second of all, the purlin and girt design was constructed. For the purlin design, we begin with calculating the dead loads of our roof members. Roof members consist of the sheeting, purlin self-weight, ceiling, insulation and service weight. Example, ducting. Other factors that were considered were the pitch of the roof, which was only 2 degrees for us, also the mass, the price, limitation supports, and the total dead load. Once the total dead load was calculated, then the total live load was calculated. For the total live load, the factors we had to consider were the wind region, the terrain category, the topographic class, the shielding class, the wind classification, and also had to use table 2.1a from the handbook. Once this task was completed, we then went on to designing and laying out the bracing. Initially, we had to arrange bracing for our shed. After that, we calculated the wind load for the ultimate limit state, followed by the serviceability limit state, and also the suction and pressure due to wind load, using coefficients found in Australia and New Zealand Standards 1170 2002. After the bracing layout was determined, once this task was completed, determining the height of the shorter wall of the shed was a quick task, which was calculated easily due to the roof of the shed being a skillion design. Then we had to find half and gable surface area. Using these values calculated, we then find the wind pressure for the roof bracing and also the wind suction for the roof bracing. Before designing the roof bracing members, we calculate the forces on the trusses using method of joints. We then go on to design the bracing members. We use the rectangular hollow sections from the Australian and New Zealand Standards 1163. These tables were attached for us by the lecturer on the Learn Online website. We go on to choose the rectangular hollow section 50 by 25 by 2 temporarily for designing of bracing, and then determine the out of plane buckling. We find that this rectangular hollow section is suitable and go with it. Then for the designing of the strut member, we use the square hollow sections. Using the charts from the attached workbook, we find the square hollow section 25 by 25 by 2 is most suitable for our strut. This option is appropriate and suitable. Once the roof bracing was complete, we design our wall bracing. When it came to designing our rafter and columns, unfortunately, due to our previous calculations in Part A of this report, many of our values were incorrect. However, we have stuck with the values and assumed that they are correct.